Hello everyone, good evening. Welcome to the third live session for the course Geomorphic Processes, Landforms and Landscapes, which is taught by Professor Javeddin Malik from Department of Earth Sciences, IIT Kanpur, and myself, Ananya P. Mukherjee. I am a PhD student in Department of Earth Sciences, IIT Kanpur. Till now, we have learnt about some of the basics about the earth as a system, the processes that are happening within the earth's surface, which drive most of the earth surface processes that are taking place. As we have learnt before also in the previous sessions, geomorphology means how the earth surface morphs itself, what are the processes that are involved in these changes of the earth surfaces. That is what we study in geomorphology. Okay. So, under geomorphic processes, we have covered till now about the endogenic processes. Okay. So, endogenic means the factors or the driving forces that are shaping the earth, those are happening in the interior of the earth. Okay. So, mostly they are slow movements or sudden movements. We learnt about the different plate tectonic processes in the previous week. We learned how they are causing mid-oceanic ridges, how they are forming trenches, how they are forming big mountain chains, large mountain chains like Himalayas. We also talked about how transform faults are creating San Andreas fault is an example of that. Okay. So, these are the things that we learned about in the endogenic geomorphic processes. Okay. Some part of it we have covered in the previous week. Now, we will start with the exogenic processes. Exogenic processes, the driving force or the agents of changes, agents which are causing the changes on earth surface, they are on the earth surface. Okay. So, they will be acting on earth material that is exposed, okay, over the earth surface. So, mostly the agents which are causing these changes are natural. Okay. Right now, with the increasing population and population density and increasing demographic conditions, obviously man-made effects are also seen, but right now we will consider only the natural agents. Okay. So, they will be causing weathering, erosion, deposition. What was weathering? Weathering is disintegration of the already existing earth material. Erosion is transferring those disintegrated material from one place to the another place, and deposition is where the transported material gets though it gets collected at one place and it forms a different geomorphic landform. Each of these processes, they will form a different kind of geomorphic landform, that is a different kind of landscape is created because of the different processes. Okay. So, there are several stages where a natural agent is going to change the earth surface, how it looks or how it appears. So, the sequence of it would be, the first landscape development it's called a geographic cycle. We had also talked about the rock cycle, the lithospheric cycle. So, geomorphology, geomorphic processes is a part of that that cycle also, and where the geomorphic processes are taking place, that is called a geographic cycle. So, the geographic cycle will depend on the structure that is already present and also the structure that is being formed at that time. The different processes that are taking place, whether it's getting weathered or eroded or deposited, and also the time duration within which a certain process is taking place. So at the start of any geographic cycle, it is called a youthful stage. Then in between it would be a mature stage, and then you have the old age. Okay, and then one more you have, that is rejuvenation. What is rejuvenation? Is that a sudden change in either the structure, the already present structure, or there is a sudden change in the kind of process that is taking place, or with respect to time, maybe there is a very sudden drastic input, or the time taken for a certain process decreases. Okay, so these are that stage would be rejuvenation. So as you can see that over here the youthful stage is in the start, like this is already a present structure. Okay, suppose this structure is present. Okay, then with time, with erosion, okay, as we reach to the mature stage, okay, we can see that with erosion the elevated lands are, they are decreasing in the height. Okay, so they are decreasing, and then you come to the C, that is your penetration. What is penetration? Penetration is, with erosion, the earth surface becomes more and more plane in nature. Okay, planar in nature. Okay, so this would be your old stage. Okay, mature stage, where there is not structures have kind of disappeared. You will see more plain features. Okay, then you have D and E, that is uplift and increased erosion. Okay, so suppose, as you can see that the red line, you can see that the red line indicates the base level. Base level as in say MSL, like mean sea level, or datum. Okay, you can see that with time, with erosion, and with the increasing stages of the geographic cycle, you can see that the top surface of the earth is going towards the base level. Okay, so with increasing stage, the elevation or the topography is going to come towards the base level of that area. Okay, so then you can see that suddenly, maybe due to some tectonic process, there is an uplift over here. So you can see that suddenly the plain area that you could see here, that has taken up an elevated state. Or you can see over here that there has been increased erosion. Maybe there was a sudden input of say water, or some other or maybe an earthquake took place and that entire area got displaced. Okay, so these changes are also affecting the way the landforms are created, the landscapes are developing. Okay, so now we come to the first kind of geomorphological landforms, or the first agent which causes or which creates different geomorphological features, that is your water water in the form of rivers. Fluvial, the term fluvial relates to rivers. Okay, anything, any landscape, whenever you call fluvial features, fluvial landforms, fluvial landscapes, they are all related to how they are being created by rivers. Okay, the pictures that are put up on the slide, they are called fluvial geomorphic features. Okay, over here you can see that the river has created very sharp or very steep kind of channel walls. Okay, this is the river channel that is flowing, and with time it has eroded the space in between the rocks over here, and it has created this channel. Okay, this is an example of a canyon. Okay, and in the right hand side you can see that it's more of the planar in nature. The feature that we see over here, it is planar in nature, but you can see there are a lot of sediments that have deposited. Okay, So you can kind of distinguish that the left hand side feature formed when the river was in at a younger stage, and the this one is mostly in its kind of the middle stage. Okay, this would be your middle stage. And then where you might be knowing the deltas that are formed, that is usually formed at the mature stage of river kind of during its flow regime. So now before we go into the kind of actions or kind of the different aspects which are going to affect how the rivers are going to weather, erode and deposit throughout its lifetime, we first need to understand some parts, or how the rivers kind of appear at different stages of its life. Okay, so over that we can we can talk about it under the river morphology part. Okay, in the first diagram, in the upper part of the diagram, you can see it is called a longitudinal profile. Okay, longitudinal profile meaning it like how it would appear from the start to the end point of a river. Okay, the starting as in where it's originating, and the end point is where it is meeting a bigger water body, mostly an ocean or a sea or a bay. Okay, so the top part, okay, is called the upper course. Okay, usually this is at a very much elevated regions. Okay, like we know that Himalayas is the place where a lot of rivers are originating in India, and also some of them flow through Pakistan also. So all these the upper course of these rivers are actually within Himalayas, so a very high elevated region. Okay, then you have the middle course. Middle course is going to extend from a slightly moderately elevated land up to the say around foothills or the plain areas. Okay, so over if considering the Indian scenario, you would consider the middle course of it, maybe coming from the lesser Himalayas, the Sivalik range, all the way up to the Indo-Gangetic plain. Okay, crossing through these features, these landforms. Okay, and then you have the lower course, which is at the the older stage of the river. Okay, so lower course is where usually you find lots of deltas being created. Okay, and meandering channels, anatomizing channels. We will learn these terms in the coming slides. So this is the basic of how the river, the flows or the kind of relation it has from the topography point of view. Okay, so the upper course is at the youth stage of the river, then the middle course is your middle stage of the river. Okay, and then you have the lower course, which corresponds to the old stage or the mature stage of the river. Okay, now below you can see there are different kinds of cross sections if we take. So suppose the river is going like this. Okay, so the longitudinal is that how it is how it looks from point X to Y. Okay, when we consider a cross section, we take it across the river channel. Okay, so A and B. So the AB would be a cross sectional section, cross sectional view of the river channel. Okay. Okay, so you have V shape, U shape, flat shape. Now these kind of different shapes or different kind of geometry of the channel beds or the cross section of river channels also depend on the stages of the river, okay, and also the kind of the structures, the geological structures that are present at that place. Okay, so the V shape is usually, it corresponds to the upper course, okay, where the velocity of the water is very high when it's flowing through the stream, okay, and it is cutting across very easily, okay, so you will get a V shape. Then you have the U shape, that is mostly in the middle course or the middle reaches that we call for the rivers, okay. So that is in the middle part. This is say the upper course or the youth stage. This is a middle course or the middle stage, okay. And as it reaches the lower reaches or the the low elevated region, or when it is approaching the old stage in its lifetime, you will get a more of a flat kind of channel bed, okay. So this would be your corresponding to the old stage of the kind of the river channel bed, okay. So over here you can see the description is given for the V shape, U shape and flat shape, okay. So more if you see from the younger phase to the older phase, the channel width increases, okay, and the depth, later on you will see, you will understand how the depth and the width of a channel also affects the kind of features that are being formed, okay. So even here you can see the kind of depth also varies with respect to the kind of stage the river is in during its flow regime, okay. Now we learned about the river morphology, like kind of how the river should appear, or how the cross section of it appears at different stages of its life. Now we come to the geomorphology, as in the kind of features that are being created by the river, okay, because of its flow, because of the amount of water that is flowing through the river through the river channel, and the kind of sediment load that it carries, okay. All these things affect what kind of geomorphic features the river is going to form, okay. in the in this image you can see that the headwater streams, okay, they are flowing from elevated areas, okay, and they cut really deep, okay. So over here, if you have ever gone in the mountainous regions, you will see that the river valleys are at much depth, okay. Like at elevated areas you can see that the river has reached quite a level of the depth, okay. So that it can erode very fast and with a lot of force in these elevated areas, okay. Obviously it takes a lot of time. All these features are formed over longer time periods, okay, but you can understand the kind of um, the kind of force that it requires to create such deep and such sharp edged river channels, okay. Then mostly you will find waterfalls and rapids, or all these kind of features in the upper part of the river course, upper course or the youth stage, okay. So most of the erosional fluvial geomorphic features are found in the youth stage of the river or in the upper course of the river, okay. Then you come to the moderate or the middle course of the river, okay, where the elevations are slightly lower, okay. Over there you can see that the valleys start kind of broadening, okay, and more streams start kind of meeting one single stream, and the drainage density increases, the drainage basin evolves and it becomes wider, okay. Meanders are one of the most important features that are formed during this middle course of the river, okay. Then you come to the lowest elevations, or where it is closer to your the mouth of the river. Okay, so where the deltas are being formed. So most of the depositional features are formed at the end or the mouth of the river. Okay, and most of the erosional features are formed at the youth stage of the river. Okay, so this is the kind of very drastic difference between the stages of the rivers. Okay, so over here mostly you will find erosional features. Okay, and over here mostly you will find depositional features, and in between you will have both erosional and depositional features. Okay, now over here when it is forming both erosional and depositional features, that time it will depend on the velocity of the river, of the water, the kind of sediment load that it carries, any kind of sudden input of water, like maybe there's floods, or there is some kind of tectonic kind disturbance. Okay, so this is how river is kind of making these geomorphological features along its course. Okay, starting from the origin to its mouth. Okay, now this is kind of a sketch of how the river channel kind of appears. This is a very idealistic kind of sketch, where at points A and B, suppose there's like a channel slope. So you can understand, like, this is a moderate slope, this is not a very steep slope. Okay, so and then you have the channel cross section. Okay, these are just idealistic. Now obviously I spoke about U shaped and V shaped and flat. Okay, those are also idealistic. That is not how it actually appears, or it you will appear like on field, but these are close approximation for us to understand that how the processes are taking place. Okay, so we can have a good virtual representation of the things. Okay, so now we come to river dynamics. Okay, so in a very easy sketch you can see on the right hand side, you have, this is your entire river system. The source is in elevated areas. Okay, this is your youthful stage of the river, this is the middle, and this is the old. And these are the kind of different features that are forming. You have tributaries joining the main river channel. Okay, then this is a confluence where where a tributary is meeting the main river channel, or maybe two tributaries together, they come and they form the main river. Okay, then this is the river, then you have levees forming, you have oxbow lakes, you have meanders, then you have deltas. Okay, so these are the very basic ones. Okay, but we'll see now how the river dynamics are taking place. Okay, how the river is make the different factors which are going to affect, or which are going to suggest which kind of features are being formed. Okay, so over here you see upstream and downstream. Okay, so this is your upstream and this is your downstream. Okay, so in the upstream you can see that the discharge, what is the discharge? Discharge is the amount of water that is flowing through the river channel at any given time. Okay, so the discharge is much lower at in the upstream areas than the downstream areas. You can see, you can also see the change over here. The river channel is very thin. Okay, but over here the river channel is much thicker. Okay, so we can understand how the discharge is also relevant to the kind of the width of the river channel. Okay, so you can see that over here you will have more amount of water that is getting discharged by the river. Then you have the occupied channel width, as I said in the previous in just now, that how the channel width is also changing with respect to its course and with respect to its reverse stages. So you can see that it is much narrower in the upstream part than it's in the downstream part. Then the channel depth also increases along the the river profile. Okay, so it is thinner in the in the upstream parts or the younger stages than it is in the older stage or the downstream areas. the average velocity of the the flow, the water flow is also much more, or it's actually in the moderate kind of a in moderate ranges between the different different stages of the river. The load quantity you can see is, the highest amount of load quantity is at the downstream area. Okay, but you can see there is an inverse relationship with respect to the load particle size. Okay, so more load quantity, but that increasing load quantity is actually of the finer materials or the finer sediments like clay and silt. Okay, so these are the things that are making up most of the sediment load in the downstream regions. Okay, so you can see that the particle size decreases when the river is flowing downstream. Also, the channel bed roughness decreases as we move from the younger stages to the older stages. Okay, roughness decreases. Why? Because the load, the particle size decreases. Okay, and with the decrease in the slope angle also, okay, it does not erode a lot, it does not make a lot of rugged kind of features as we go downstream. Okay, so this in a gist gives you the kind of differences or the how the factors differ when we are moving from the younger stages to the older stages of a river profile. Okay, now in the image over here you can see a relation between the water that is flowing and its velocity with respect to the channel geometry. Okay, so obviously there is more friction at these edges, or the channel edges. Okay, so obviously the velocity or the flow will be slowest, okay, wherever the water is in contact with the river channel, and in between, like above that layer, you will have the faster flow. Okay, so this is your basic physics. Okay, now this is when it's kind of an even, it's flowing in a straighter channel. Okay, the B will show when the river is turning. Okay, so when the river is turning, okay, the water is turning, you can see that this area is going to get eroded. Okay, you can see over here, this are the flow. Okay, so the flow is getting the the flow will be slower in the inner side of the channel. Okay, and in the outer side of the channel, okay, it is going to be greater. So this part will get eroded, this channel will get eroded, and all the so whatever sediment it is carrying from here, this will get deposited in the area where the flow is slower. Okay, this only happens when the river is bending at a place. Over here you can see in the A cross section, okay, there is no deposition as such because the flow is kind of uniform. Okay, it will erode, the erosion is uniform across the edges. Okay, but over here you can see that the fastest flow is in the outer part. Okay, the where it is curving, the outward curve, and you can see that the flow is slower in the inward, in the inside curve. Okay, this is where your depositions will start taking place, because the relative flow of the water in the same channel at a time is differing. Okay, over here as I have mentioned that when a stream curves, the flow of water is faster on the outside of the curve and slowest in the inside of the curve. Okay, when the stream is straight, it is uniform. Okay, uniform, but the upper layers are going to flow faster than the ones that are in contact with the channel bed. Okay, and this is one of the first effects that we see, or one of the first ways that the rivers erode and deposit as per the changes in the flow, the velocity. Okay, So this happens, any system, as even we have spoken before, that any system needs to be in balance. Okay, so the amount that it is eroding, okay, and the amount it is depositing, there needs to be a balance between the two for the channel to be in kind of an equilibrium state. Okay, equilibrium state, or it is its ability to kind of uh, adapt to the changes that it is going to experience while flowing from one place to the another. So one of the first things that is going to affect the way the water is flowing is obviously gravity. Along slope, we know that due to gravity, something from a higher level is going to flow towards a lower level. Okay, then you have the frictional forces, the friction that is being offered by the channel bed, and the between the water that is flowing and the channel bed. Okay, and within the flow itself, where over here we've spoken about how part of it will be fast and part of it will be slow. So these are some of the things that are going to affect the way the river is going to change the shape of the earth surface or the landforms. Okay, next we move to the kind of particles or kind of sediments that are going to be transported by the river and also deposited by the river. Okay, so the primary erosion is happening, in the downslope or in the upstream areas, okay, where the water is mostly eroding, the river is mostly doing erosional work, okay, and the sediments that it is eroding, it is going to carry from the upstream areas to the downstream area. But only some part of these sediments is going to form the drainage basin that we see. Okay, because most of the sediments, they start depositing as and when the flow the the speed of the flow changes of the river water. So it will start depositing, and then that also depends on the kind of sediment it's carrying, the velocity of the stream. Okay, so that is important to know that what kind of sediments you'll find where getting deposited or getting eroded. Okay, so over here you can see the types of sediments that are being carried by the river water. You have the bigger grains, okay, over here, and then you have suspended ions, okay, and then you have particles in suspension and ions in solution. Okay, some part of it is not going to get deposited anywhere, it is going to stay within the water, okay, where it has mixed with the water. Then you have very fine silt, very the very fine clay grains, okay, they are also mixed in the water. They get deposited when the flow is really slow. Okay, over here you can see saltation and traction. These are the modes of transportation of heavier sediments along the channel bed. Saltation is where suppose a smaller kind of sediment gets bounded off from here, it will strike here, then it will it will bounce off, and then it will go ahead and fall somewhere where it finds a place when the water is flowing. Okay, so the flow is not linear, it is mostly kind of a wavy thing or a turbulent flow. So with the flow, the sediments are also flowing. And then you have traction. Traction is that when sediments are dragged along the channel bed. Okay, and then you have suspension. Obviously, as I said, the finer materials are not getting deposited, or they are not being transported along the channel bed. It is suspended in the water that is flowing through the river channel. Okay, you can see that there are three types. You have bed load, you have suspended load, and you have the dissolved load. Okay, so these are the kind of sediments that we see. These are also affecting the way the river is going to create geomorphological features. Now we come to a very important, kind of figure that gives us an idea about when the river channel is going to erode, when the river channel is going to transport, and when the river channel is going to deposit the different sediments that it is carrying. Okay. So, considering the particle size and the flow velocity of the river channel. Okay, particle size of the particle size and type of the sediments that are being carried by the river, and also the flow velocity of the river. According to the the diagram that is over here, you can see that the finer ones, okay, so the finer ones are transported, okay, transported even at higher flow velocity and at lower flow velocity also. Okay, so these are always mostly getting transported, okay, and these are eroded all along the particle sizes, okay, sorry, like these are eroded at very high velocities, you can see over here, and at the lower velocities, okay. Then particles getting eroded, okay, so the erosion happens at higher flow velocities, okay, over here you can see, and mostly the at moderate flow velocities also you will find silt and sand particles will also get eroded, okay. And you can see that the transport, the curve, the area between for the particles being transported becomes narrower and narrower, okay, as the particle size increases, okay. Then you have particles deposited. You can see that the larger particle size, the larger particles or the larger sediments, they start getting deposited at very low flow velocities also, okay. So this diagram gives you a relation between the different the sizes of the of the sediments, and also how it is getting affected by the flow velocity, okay. So with this diagram, if you try to understand how the river channel is going to act at a younger stage, okay, so it will mostly be transporting, okay, it has moderate velocities, okay, it will transport and it will erode, okay, all the material, all the particles, okay, it will hardly deposit anything, okay. But if you if you come to the middle reaches, okay, the middle part, you will see that the particles, as the flow velocity kind of starts decreasing, you will see that the particles will start getting deposited, okay. So the first particles that would get deposited are the the larger sediments, okay. Then when the flow velocity decreases further, then you will have the consecutively the smaller grains, then you will, the sand will get deposited, and at the last, most of the when the flow velocity is very low at the mature stage, okay, a lot of clay and silt is still in the water. Some silt, some grains of silt will get deposited, okay. And you can see that the clay is actually kind of never deposited. Clay is still being transported, okay. The clay is still kind of dissolved in the water, or it is suspended in the river water, okay. So you can see that you have the two curves that are important for us to know, okay. One is your erosion velocity curve, and the next is the settling velocity curve, okay. So this is the erosion velocity curve, and this is the settling velocity curve. So this will give you an idea about how the particle size, as large it is, the the faster it will get deposited, okay. And the smaller, or the moderate sized particles will get eroded up to even moderate velocities. So any particle that is kind of in between the two curves, it will be either moving too slow, or it will be too small to be eroded or deposited, okay. So it is mostly getting transported in the stream only, the all the particles that is kind of falling between the two curves, and in the flow regime between the two curves. So now we learned how particle size or sediment size and the flow velocity of the channel affects the kind of features that are being formed by rivers. Now we come to how kind of increasing discharge or increasing water levels in a river channel, okay, could cause different kind of geomorphological features. Now suppose you are considering the flood stage in a drainage basin. Okay, so one of the main factors is the, the discharge, the volume of water that is flowing through the given river channel. Okay, so with seasons also this discharge varies. Okay, obviously in the rainy season you will have more discharge. Okay, and in the drier seasons it will be less discharge. That itself is going to change how the river channel looks. Okay, then obviously climatic variations, weather variations, places which are more frequently flooded, and or the places where you have more of dry spells, more of droughts, all these conditions are going to affect how your river is getting how your river geomorphology is taking place. Okay, so you can see over here in this diagram, okay, suppose this is your bank full stage, okay, and then you have the flood stage. We learned before this, when the flow velocity is more, okay, most of the sediment that is present is going to get transported or eroded. Okay, so the flood stage, you can see that the water increases, okay, and it spreads on the sides. In the flood stage, the after the water has spread, okay, so it will sit for a while. Okay, when it is flowing up, and then when it is spreading across, that is the time when your material start depositing. Okay, so coarser material is not going to be able to flow to the sides, because as the water is rising and moving, the most of the velocity is decreasing as the water moves away from the channel edge. Okay, so you can see that the coarser material is getting deposited first, then you have slightly finer, and then this is the finer and thinner sediments. Okay, you can also see that the kind of the thickness also varies. All this is again being affected by the flow velocity of the water, by the particle size that is in the particle size of the sediments that is in the water, and also now at the stage of the the bank full stage. Okay, yeah, no issues, Kuldeep. Thanks for joining. Even if you are late, there's no issues. Okay, so we are still at the basics. Okay, and then you see that with repetitive flooding, okay, so the material over here gets built up. Okay, so more as the natural levees, as this feature is called, okay, if the natural levees kind of increase in height, you can see that then for probably in the coming year, if the flood is happening and the discharge is only till the water is only till here, you can see that this area is not going to get flooded anymore. So natural levees, when they are forming in the normal seasonal variations, they are going to act as embankments, and they are going to prevent flooding in the the floodplain region. Okay, so and this area, okay, is going to remain in the fine sand, the fine sand is going to remain over here. Obviously the other kind of a thing is that the fertility also kind of depends on the sediments that are getting deposited along the flood plains. Okay, so as we even mentioned that these these are very delicate balances. Okay, in nature this balance is held in position, but due to the uh, human activities, the increasing human activities, human interferences has been changing this balance between the bankful stage, the flooding stage, the formation of the embankments, the transport, to the extent to which the deposits are taking place. Okay. So you can see over here that it is mentioned that the development of natural levees during flooding of a stream, it becomes the finer particles are always deposited away from the river channel bed. Okay, that is where the river is flowing at the current time. So now we come to a few, mathematical equations that are going to, make you understand, the how we can understand the velocity of the river channel at one point, and all the kind of, how much discharge there is in the river channel at a certain time. Okay, so we use Manning's equation. Okay, using Manning's equation, we can, kind of calculate the discharge, that is volume of water that is flowing across the river at one particular time. Okay, so mostly your Manning's equation is going to it's dependent on the hydraulic radius, the hydraulic radius, the water surface slope, and the roughness coefficient. Okay, so you can see that more the roughness is going to lower your velocity. We saw this in that upstream downstream diagram also. Okay, that average velocity is lower in the in the upstream areas where you have more channel roughness. Okay, and you can see that it depends on the hydraulic radius and the water surface slope. So hydraulic radius is, it is actually it depends on the cross sectional area and the perimeter of the wetted perimeter of the channel. Okay, so the hydraulic radius, if that is more, your velocity is more. Okay, so this is kind of the relation between the velocity of the flow velocity of the water, and also the different kinds of factors that are affecting it. And then the discharge is again, uh, dependent on the similar set of coefficients over here, you can see, and also it depends on the area, the cross sectional area of the channel. So now we come to another numerical value that is it will help us to understand the the type of flow that is there at during the river course, during the course of the river. Okay, so that is the Reynolds number. Okay, it will predict the extent of turbulence that is there in the fluid. Okay, so this is the equation for it. So it depends on the flow velocity, the characteristic length, and like it depends on the geometry, the depth, and the fluid density, and the fluid viscosity. And in general, it will depend also on the kinematic viscosity. Okay, so this is the equation for the Reynolds number. What is important for us to know, that if you calculate this, you have to see that if the Reynolds number is greater than 2000, it's a turbulent flow. If it is less than 500, it is laminar flow. Okay, so you can see over here, this is the distinction between the laminar and the turbulent kind of flows. And again, using the Hulstrom Sundrum the diagram that we discussed before, you can see that the Reynolds number is also going to affect the kind of process that is happening, like erosion or transportation or deposition. Okay, so boundary Reynolds number, you can see that if it is lower, then it is hydraulically smooth. Okay, in between it's transitional, and then you can see it's hydraulically rough. Okay, now we come to another kind of factor that is affecting the middle course of the river. Okay, that is the river sinuosity. Okay, so river is usually, it can be straight. Okay, it can be a slightly curved. Okay, or it can be very much curved. Okay, you have seen these things, you know, it's or else what you know is like, you know, kind of there are some deposits here and then the river is flowing through those deposits. If you have ever traveled across the country in trains, you will mostly kind of, you know, see some parts of the rivers looking like one of these, you know, kind of it will be in one of these natures. Okay, so what is governing these this sinuous nature of the river channels? Okay, so this again depends on the flow velocity, the sediment load that it has, okay, the discharge that is in the river channel. Okay, so how do we calculate a factor that is called sinuosity ratio, that is the length of the stream channel. Okay, so length as in the absolute length, if you measure as the channel is flowing, okay, along the along the you know, suppose you just take one part of the channel, okay, and you measure the exact length of the channel, okay, and divide it by the distance between the two points, the straight line distance, okay, between the two endpoints of that stream that you are seeing, okay. So that is going to give you the sinuosity, okay. This is the sinuosity number. Now when we consider the ratio, okay, why the ratio is important for us, like even within one river valley, okay, you will find that some segment, the you know, if you consider say 5 kilometer stretches, okay, 5 kilometer stretches of the river channel that is flowing within one valley, you will see that after 5 kilometer also the sinuous nature of the channel is also changing. Okay, suppose you're considering one river valley that is, you know, in the closer to the upstream areas, and then you're considering the reaches that are in the middle and closer to the older stage. Even though it's of the same river, you will find that the sinuous nature of the river changes from the upstream areas to the older to the downstream areas. Okay, so we need to understand, why do we need to understand the sinuous nature? Okay, sinuous nature is going to help us to understand the erosional you know, erosional activity of that river channel. It will tell us whether the river channel is, you know, prone to shifting in that river valley. Is the river valley going to get extended beyond its current you know, drainage divide, or is it going to, you know, invade the you know, the neighboring drainage basin? Okay, so these things are important for us to know, for us to understand the you know, the river, the migration of the channels that we are going to study, like that I am going to explain channel migration also. So sinuosity or the sinuous nature of the channels is going to help us in determining these things also. Okay, so sinuosity ratio is the channel length upon the valley length. Okay, so this is again similar to this only, okay, but now we are considering the valley, okay, and these could be done in smaller segments, okay, and this can be done at a larger segments also. So if your sinuosity ratio is below 1.1, it's a straight channel, okay. You will see most of these occurring in the upstream areas. Then sinuous in nature, you will find 1.1 to 1.5, and then you have the meandering nature, that is going to be more than 1.5, okay. And we will see how even from meandering point it can go back to being straight again, okay. This effect is also due to the you know, depositional and the erosional nature of the riverbed, okay. So now over here, if you see, these are the stages of a river channel going from a straight river channel to a meandering river channel, okay. So this is your, it looks straight, okay, but you can see over here that you have depositions, okay, and you have some riffles and pools. Riffles and pools are, you know, erosional features that are created in the channel beds, okay. You can see then the number of riffles and pools are increasing, okay, and the deposition is also increasing, okay. It will start eroding more of this area, this area, this area. Okay, then it will, then you can see that with erosion the channel is, you know, bending more. Okay, these are inflection points. Okay, these are where you can see that this is where the bends are happening. Okay, so with time more erosion is going to take place in these areas, and the more sinuous this river channel is going to become. Okay, see over here the meandering channel pools are 1.5 times in length. Okay, over here if you, obviously this is a, you know, estimate of how the channel is, you know, uh, also you can see that the channel length is increasing. Okay, as and when your sinuosity is increasing. Okay, then you have additional riffles and pools. That means the erosion is, you know, extending beyond what in what you can see in the current stage. Okay, and it is getting more and more sinuous in nature. So this is probably happening at the youth stage. This is also at the youth stage. Then you can say that this is, you know, happening when the upstream, you know, kind of, you know, lower elevated areas, and this is probably happening in the plain areas. Okay, so these are happening in the elevated areas. This is lower elevation, and then this is the plain areas. Okay, where it is, where even with, you know, the velocity is enough for it to erode the you know, the softer sediments that are, you know, forming next to the river basin. Okay, so based on the sinuosity, based on the sinuous nature of the channels, you can have different kinds of channel patterns. Okay, so as I have mentioned before that the formation of a channel is going to be a function of the water, flow velocity, the sediments that is being supplied to it and transported by the channel. Okay, and at any, at, you know, at a certain reach, the this you need to remember. Okay, when you're studying about river geomorphology, the water flowing at any certain point is going to take the easiest route available to it. Okay, so suppose you have kind of a harder rock, the, or say rock which is, you know, which is going to take much more force for it to get eroded, and there is a softer sediments or loose sediments that are in your on the other side. Okay, so the river channel is going to try to maintain a, you know, a low energy state. So to maintain that low energy state, it will not go through that you know, hard rock, or, you know, where you have more amount of material to erode so that it can pass through. It will erode the area, or it will flow through the area where it can easily, you know, just make its way and flow across. Okay, this is one of the reasons where the river channel is going to try to maintain a low energy level. Okay, where it is sustained, where you know, the flow of the water does not need to be increased. Okay, on its own. Okay, so the river channel is always going to follow that path. So that also affects the kind of, you know, the sinuous nature that we are talking about. So over here you can see that the different channel forms are there. Okay, so you have a straight channel where you have a very low sinuosity ratio. Then you have a sinuous channel, then you have, you know, meandering river. Okay, you can see that even you have another index called braiding index. Why braiding? Because, you know, there are many depositional features that are that are forming within the river channel. Okay, so as these as the number of these deposits increase, you can see that the braided index also increases. Okay, so you can see that the, you know, over here these are small, these are smaller you know, depositional, you know, features compared to the stream length, but the number is very high. So this would be a braided channel. Okay, like this is much braided. Okay, and braiding also starts with the meandering the meandering process. Over here you can see that this is going to give you an idea about the relation of the different channel forms and the kind of channel, the different aspects of the channel. Over here you can see that with decreasing channel stability and increasing sediment supply, you are going to have more braided channels. Okay, and this is what do you call as bed material. Bed material is most of the the coarser sediments. Okay, so the coarser sediments would be called bed material. This is mixed, and this is mostly your kind of dissolved material or the suspended material that is present in the channel. Okay, so if you have more of boulders and cobbles, that is larger sediments, so you will find such kind of channel forms. You can see that it with increasing sediment supply, it will become more and more braided. Okay, and over here you can see the other relation, that is your increasing channel gradient, increasing channel decreasing channel stability and increasing sediment caliber. What is sediment caliber? It is kind of the the carrying capacity of it. Okay, so this is one of the ways you can understand that how from with increasing sediment supply and also decreasing channel stability means that the channel is going to change its path very much often. Okay, as I said, it is going to try to stay in that low energy state. So whichever path it feels at that point of time that this is going to take less energy for me to go from here, it will take that path. Okay, so that increase that is kind of decreasing your channel stability. So you can see from straight it will go to a more sinuous nature and then it will go into the braided stage. Okay, and this depends on the type of sediments also that are present. So these are kind of different channel patterns. This is kind of the trade-off between the erosional features as well as the depositional features that we see through a river's through the course of the river flow. This is a table, okay, where you can understand the different kinds of channel styles based on your channel type, then your the kind of fill, what is the composition of channel fill, as in the the kind of sediments, the types of sediments that are found. Then you have the channel geometry, the internal structure and the lateral relations. Okay, so let's go by one by one. Okay, so suppose we are talking about a bed load channel. Okay, so bed load channel means it has more of the bigger particle size sediments. Okay, so the bed load channel, so you can see that it is dominantly made up of sand. Okay, the channel fill, the the channel, the place or the region where it is flowing through has mostly sand. Okay, then the cross section of bed load channel will be the width is going to be much larger compared to the depth of the channel. Okay, and this usually occurs in the low to moderate relief. Okay, and mostly this is going to give you a straight to slightly sinuous nature in the channels. Okay, then if you come to fabric and infill, okay, these are much more detailed kind of geomorphic study related aspects. So just you can understand that the accurate most of the material that is getting deposited, it's going to depend on the, it seems so confusing. See, you just have to kind of understand that when your channel fill is it has larger particle size, okay, it will be called a bed load channel and it will be mostly straight in nature. Okay, we are only talking about the channel form or channel pattern. All the rest of the things you don't need to remember right now because that is not kind of taught. Okay, I have taken this image because this shows the the diagrams are very easily understandable. Okay, so you can kind of not pay attention to anything that is given after the map view. You only understand the first, 4 columns of this table. Then you have the mixed load channel. Okay, so that is when you have a mix of different particle sizes. Okay, where you can see that the width and the depth are kind of, it's relative to each other. Okay, and then you can see that the channel is much more sinuous in nature. And then when you have more of suspended load, that is finer particles, okay, the finer particles and some particles that are dissolved in the water, okay, you can see that the depth is lower, the depth also varies. Okay, so it has low to very low width slash depth ratio. You can see that the depth is increasing. Okay, so if the depth increases, the ratio is going to decrease. Okay, over here you can see this has high width to depth ratio. So this channel, the bed load channels have lower depth, okay, lower depth, but it has higher width. Okay, in the mixed load channel, it is in the middle. Okay, so like both of them are, approximately equal to each other. Okay, sorry, depth, this will be width is almost equal to the depth of the channel. Okay, over here you can see that the depth is higher, okay, and the width is smaller. You can see that, there are two different kind of the smaller, you can see two channels over here. Okay, that is because, it's forming these braided rivers. Okay, is this easier to understand, Kuldeep? I think Kuldeep had kind of a doubt. Is this easier to understand? Like when I talk in terms of the kind of sediments that are in there, and the depth and the width, and then how it is going to appear. Is this understood, or like should I explain this again? Okay, it's still confused. Okay, I'll go back to the previous slide then. Okay, did you understand this one? I'll just, okay. So at the start, you have the river flowing. Okay, obviously it's not going to be entirely straight, but it's mostly straight approximately. Okay, yeah, so I'll just explain. Okay, so over here the flow is happening like this. Okay, it is mostly eroding and carrying sediments with it. Okay, now when it comes to lower elevated, okay, so youth stage of the river is when the river is originating at higher elevations. Okay, then it is, coming down, at lower elevations, and then it reaches the, say ocean or bay or sea. That is going to be the mouth of the river, and that is going to be the older stage. Okay, so throughout the river course, it is going to either erode or transport, or it is going to deposit the sediments that it is carrying. Okay, so now if this is a straight channel, okay, so as and when the velocity changes, or the kind of the sediment load is increasing, okay, the material that the water is carrying with it is increasing, so it will start depositing. Okay, so when it deposits, the nature of the deposition is that, okay, in the outward curve of the river channel, it is going to get eroded. Okay, and in the inner curve of the channel, it is going to get deposited. Okay, so again, this is your outer corner, it will get eroded, and material is going to get deposited in the inner curve of the channel. Okay, now with time, okay, so these deposits are going to increase. Okay, so how will this look then? Okay, it will start curving more. Okay, it will start depositing more over here. Okay, and when this part is getting deposit, when material is getting accumulated over here, it is going to be harder for the river to, flow easily from this part, so it will start shifting. Okay, it will start shifting, it will start eroding this area. Okay, this will again over here also, this part is going to get deposited. Okay, more the deposits are getting accumulated, and then this part is going to get eroded. Okay, Then with time this will become more and more bendy in nature. Okay, that is what we call as a meandering river. Okay, so then it will become like this. Okay, so the river is going to flow like this. Okay, as you can see that, you know, this part is the deposit part, this part is the deposited part. Okay, slowly its erosive power is going to decrease. Okay, and then with time, as I said, as the erosive power is going to decrease. Okay, so it cannot flow so much anymore, it is not going to take this longer path. What it will do is that it will leave this flow area. Okay, it will leave this flow area, and then again it will start flowing as a sort of a straight channel. Okay, so you can see how the sinuous nature of the river's channel is, is changing with time, it's changing with the flow velocity, it's changing with the amount of sediments getting deposited and how much it can erode. Okay, so this is the only thing that I am trying to explain. Okay. Okay, so over here you can see in this diagram, at first you have the sediments, you have the straight channel. Okay, and then with time more and more more and more sediments are getting deposited. Okay, as and when the sediments are getting deposited, you know, it is going to find narrower paths to flow between the deposits. Okay, so this is how the channels are going to look with time, with increasing sediment supply and decreasing channel stability. Is this clear now, Kuldeep? Did you understand what I am talking about when I am talking about the channel patterns and channel forms and how they are, getting shaped? Okay. So in this diagram, in this table, don't get very scared about the, kind of columns after the fourth column. You only concentrate in the first four columns. Okay. Now we come to the effect of tectonics on the, river profile. Okay. Or, this is kind of the Indus Valley profile. Okay, so somewhere around here it is becomes braided. Okay, then it becomes anastomosing. Okay, then you see that over here the channel gradient is increasing. Okay, so the channel gradient is increasing, the flow velocity kind of increases compared to the place over here. Okay, and over here it is showing the, you can see that the upward arrow is the uplift and the downward arrow is subsidence. What is uplift? Any area is getting, elevated, and subsidence is any area getting, it is going down or it is getting depressed. Okay, so at lower gradients you are going to have this anastomosing kind of channel. Which one is the anastomosing? You know, this would be called an anastomosing channel, these two, braided or anastomosing. Okay, you can call this as the over here you can see this is the anastomose channel. Okay, this is your braided channel, or it can also be anastomose channel if the, the river, the water channels become very thin. Okay, as you can see that as the, the channel slope over here increases, you can see that with increase, with slight increase in the flow velocity, now the river channel is getting less sinuous in nature. Okay, compared to this anastomosing channel. Okay, then again when it comes to, another subsidence kind of a thing. Okay, so over here again the flow velocity kind of decreases. Okay, so from meandering to it is, changing to straight. Okay, so effect of tectonics is also going to change your channel pattern or channel form. Okay, and that again is going to change whether your, river channel over there is eroding the material or it is, depositing the material over there. Okay, over here also you can see that suppose, uh, this is your plane. Okay, migration of meander belts. Okay, so suppose this area gets subsided, or there's a fault and this area has gone down, okay, then what happens is the meanders are going to get slowly separated with respect to the kind of the change in slopes. Or suppose this was where the channel was first flowing, where it formed these meanders, okay, then slowly the channel shifted, then again with say subsidence this channel shifted here, and now the channel is over here. Okay, so if you suppose you are in an area, you can see a lot of such oxbow lakes, or you can find these depositions, following this kind of pattern. You can see that you can say that the channel has moved from one place to the another, or the meandering part of that river channel is moving from one place to the other, which is in response to the changing changing elevation over there, or changing topography over there. Okay, so these are external basin controls, uh, and this will affect the channel patterns or the channel form that is forming in that region. So now we understood, till now we have understood how during the river's course, or during the different stages of the river's life, okay, how it acts with respect to the erosional process, or the transport process, or the depositional process, okay, and these are affected by the flow velocity of the flow velocity within the river channel, of the water, of the sediment supply, of the different types of sediments that are being carried by it, by the amount of discharge that is that is existing at any given time through a river channel. Okay, and also we understood how changing between the erosional nature and the depositional nature of the river is going to affect the kind of features that are being formed. And also we understood, we saw that how the changes in the tectonics, changes in the elevation, changes in the uh, mm, slope, the channel slope is going to affect the formation of different channel patterns. Okay, so these are some of the basic things that we saw about the river dynamics. Okay, uh, in the previous slides till now. Now we come to the different features that are being created due to these actions of the river channel. Okay, so over here you see that this is an example of a canyon. Okay, so the different features that are formed by the river. Okay, this is after a long time. Okay, we have spoken about the geological time scale. So remember that these processes are not sudden. These have formed over millions of years, billions of years, thousands of years. Okay, so these are not very just formed in within 1 year. Okay, these take time. So you can see that currently the river is flowing over here. Okay, but these canyon walls, okay, they formed much in the geological much before in the geological past. Okay, so first the canyon walls uh, they were formed, and then you can see that at when these plain areas are formed, okay, you can say that the river was flowing at a kind of a quicker stage. It is just it didn't form a lot of the probably the elevation or the slope over here had not changed. Okay, then again probably the slope changed. Okay, and the velocity also kind of increased, or the sediment load decreased, so it eroded more than it deposited. And then now you have the floodplain. Okay, you have the inner active channel, then you have a point bar, you have levees. Okay, natural levees over here. Then obviously you could have the action of wind also in the same river valley or the canyon area. Okay, so this is an example of how a canyon floor would look like. Okay, so this is just this is an example. Okay, then another erosional feature that we just spoke about, like where I explained with the diagram over there, is the formation of the oxbow lake. Okay, so at first the river is flowing as a meandering channel. Okay, and these are called the meanders. Okay, you can see that these red spots over here, or the red features over here, these are the depositions. Okay, I'm sorry, these are where the erosion is taking place. Okay, these red areas are where the erosion is taking place. Okay, and over here you can see that the point bars are forming in the inner curve of the river channel or the meander. Okay, and soon you can see that because the erosion is at first the erosion was here. Okay, now the erosion is moving over here. Okay, soon this area also gets eroded away. Okay, when this area gets eroded away, the channel then becomes a straight channel in this region. Okay, as I said before, the channel is going to try to move along the path where it will keep a low energy. So it will flow in this straight channel and it will stop supplying water in this bend. Okay, it will not flow through here. Okay, soon you will see that now the deposition is it will start happening here and here. So this point bar that is created here is going to join. It is going to cut off this water, this meander from the constant water supply. Okay, and then it will form what is called an oxbow leg. Okay, and this area is going to get deposited and this area is going to stay like this. This is not going to get any more water supply. So oxbow lake is formed by both erosional nature of the river channel and also the depositional nature of the processes that are carried by the river channel. Another erosional feature that is formed during the course of the rivers life are the different kinds of river valleys that we see. Okay, so at first it will river will cut down and it will deepen the valley. Okay, and then the valley will start it will start widening with time. Okay, and as you can see, as and when the channel widens, you see that the water the stream starts taking a meandering pattern. Okay, at first there is not much area for it to meander anymore. It will flow as a straight channel, then it will become slightly sinuous and then it becomes a meandering channel. So this is how river valleys develop. Okay, and another example, as we all know, is the waterfalls and rapids that we see. These are also erosional geomorphic features of fluvial nature. Okay, so these usually happen in the elevated areas. The water is flowing, it is going to start cutting the rocks. Okay, over here you can see that the water that is falling over here is going to erode this area. Okay, and then it will it's mostly due to the sudden drop in elevations, sharp changes in elevations. Okay, so these are the areas where you will find your waterfalls. And another kind of feature that we see are rapids. Okay, rapids again are going to be due to the uneven slopes that are experienced or that are met by the river channel during the course during its course. Okay, now we come to another important aspect of fluvial geomorphology, that is the drainage morphometry. Okay, one of the important numerical terms is the bifurcation ratio. What is a bifurcation ratio? It expresses how much a river or a stream or channel has branched out during its evolution. Okay, it is going to give you an understanding of how dense the drainage system is. Okay, we call it the drainage density. And how do we calculate the bifurcation ratio? Before that, we have to understand what are stream orders. Okay, when suppose this is your a drainage basin, and this is a kind of pattern that you see. Okay, so the lowermost, or the shortest uh, length of the streams, okay, where they are not bifurcating anymore. Bifurcating as in they are not dividing anymore into smaller streams. Okay, so this is the first order stream, okay, which is not bifurcating. Okay, then when two first order streams join, it forms a second order stream. When two second order streams join, you get a third order stream. Okay, so this is how it goes. So over here, one first order and the second first order stream join, and this becomes a second order stream. Over here, the two second order streams are joining to form a third order stream. Okay, now over here it is 3 and second one is joining over here, so this still remains a third order stream. Okay, over here a first order stream is joining a third order stream, and it will remain as a third order stream. Okay, when two similar order streams are joining at one place, it will form the higher order stream. Okay, now this is where you have very few streams of the different orders. Okay, but when you consider this drainage basin, you can see that there are the number of streams of the different orders are increasing. Okay, so there are so many first order streams, and then they are joining together to form the second order streams. Second order streams are then joining to form third order, then the third orders are forming the fourth order. So you have to calculate in the opposite direction. Okay, so you first start with your smaller order streams, and then you go to the higher orders, and then the order that is the final higher order that is remaining, that is the kind of the order of the entire drainage system. Okay, so this is a fifth order drainage system, this is a third order drainage system. Okay, so what is bifurcation ratio? Okay, this is going to give you an example of the drainage density. Over here you can see that the number of first order uh, you know streams is less than the first order streams over here. So subsequently the bifurcation ratio, okay, is going to be lower than this, and if the bifurcation ratio of this is lower than this, that means that this is less dense and this is more dense. Okay, so this is how drainage density is going to differ with respect to the bifurcation ratio, and which is again dependent on the number of the different orders of the stream. Over here you can see that drainage density is also it's a ratio between the total length of the different order streams, okay, and the drainage basin area. Okay, so if you have more number of different order streams, obviously your the total length of all the streams is going to increase. Okay, and if the area is smaller compared to the number of different order streams, obviously it is going to give you a much more denser drainage basin. Okay, so this again is going to reflect which stage your river is in. Okay, which is basic understanding with how much we have seen till now. You can say that this is going to form in the youth stage, okay, where it does not have a lot of area. Okay, it will just flow in straighter channels. Okay, and it is going to go, obviously to certain extents it will form the second order or the first order streams. Okay, and this could be forming at the middle reaches, or a much more denser kind of drainage basin can form at much towards the older or the mature stage of the river. Okay, So as I just explained, this is how the drainage evolution would take place. At the youth stage, you will have a lower density, okay, and then the drainage density increases, okay, and over here this is the maximum extension, and this is where your drainage density is probably the maximum, okay. Over here, as you can see that there is integration and channel loss, okay. So what is channel loss? That maybe some of the lower stream order streams are going to lose water, they are going to get dried up, the water supply is going to get cut off, so these streams will no longer be active, okay. And there is going to be probably suppose the stream of one particular stream of the other drainage basin kind of gets connected to this drainage basin, okay. So the water will kind of get supplied from here, maybe it will get capture, it will, the stream will get captured from the different drainage basin, okay, then that part will get cut off, okay. So this also is one of the part of the drainage basin evolution, okay. So you can see it goes from youth to mature, where you have the maximum extension, and this is probably where towards the mouth of the river, or just close to the mouth of the river, this kind of evolution can take place. Now depending on the, okay, so if the bifurcation ratio increases, density will increase or decrease. Bifurcation ratio will give a slight indication towards your drainage density, but your drainage density will also depend on the area, okay. Maybe obviously if it has more bifurcation ratio, that means it has more number of smaller orders, smaller stream order streams also, okay. So that requires a larger area, okay. So that means if there is the higher bifurcation ratio is going to indicate that the drainage density is also high, okay. Is that clear? I think Pravesh asked this question. Sorry, Pooja. Yeah, did you understand, Pooja? The bifurcation ratio, if it increases or if it is more, the density is also more, the drainage density is also increasing.
Yes, ma'am.
Okay. Okay, so now we come to different kind of drainage patterns. Okay, now drainage patterns is also going to is obviously it's affected by the drainage evolution, and drainage evolution that is being affected by the kind of rocks that are present over there, or the kind of structures or geological features that are present over there. Okay, so this is just a smaller example. This will be taught more in detail in the I think upcoming week content that is there. So again this will be taught, and more drainage patterns. This is just an idea. So you have generally you have dendritic pattern, you have rectangular pattern, you have radial pattern. The second diagram, uh, okay. And yeah, actually kind of not exactly plate boundary, but due to the tectonic activities, your drainage pattern can either evolve or change in its orientation and spatial kind of extent, okay. So you have dendritic pattern, you have trellis, you have rectangular, you have radial, okay. So these are some of the common ones that we see. You can see that examples, the dendritic pattern is like a tree, then you have the rectangular, that the bends that you see in the river channels or in the stream channels is going to be at 90 degrees. Then you have the radial, okay. So radial is like that one central point, okay. Either all the rivers are flowing towards the central point or away from that central point, okay. So it can happen in a dome kind of area or in a basin kind of an area. Then you have the trellis, okay. So trellis kind of it occurs where you have alternating weaker and harder rocks. Okay, so it will find the weaker rocks and it will flow through the weaker rocks. Okay, and suppose there is a joint between connecting the weaker rocks and the weaker rocks through the hard rocks, so it will flow through that joint also. Okay, so I have also mentioned some of the examples of these drainage patterns over here. So you can kind of google their images and see how they look in real life. Okay, so then we have some other drainage patterns. Okay, so collision, transforming plate. Yeah, it could actually look like the transform plate boundary, but that is not the case over here. Okay, the transform plate boundary actually where over here, as I will talk, okay, you have concordant drainage patterns, you have discordant drainage patterns. Okay, what is concordant drainage patterns? That it does not change. Okay, whatever is the trend of the area, the drainage patterns are going to follow that trend. What is discordant? Discordant means that the previous trend of the drainage pattern or the area is disturbed. Okay, so discordant means disturbed. It is going to change with respect to the disturbance that is the kind of there, and it might not be relevant to the rock structure that is present there. Okay, so previously there might have been a different kind of a pattern, and but now there is a different kind of a pattern. Okay, so concordant, it's going to follow the trends of the area that is present, and in the discordant it is not going to follow the trend. Okay, it might have got disturbed at any point of time. So in concordant you have the consequent, subsequent and the obsequent stream and the recipient streams. Okay, so consequent is obviously it is that direct consequence of the topography that is present. Okay, subsequent is after the consequent trend it is going to follow through that consequent and subsequently these kind of streams. Okay, so you can read the matter over here, so you can understand the difference between what is a concordant and the discordant. Okay, in discordant what is important to know are like the superimposed drainage and the antecedent. Okay, suppose there was an existing drainage pattern, okay, which was kind of then changed due to the erosion. Okay, and now the stream is, the drainage pattern is slightly different. Okay, so erosion has caused the difference in the two, you can see probably two different kind of drainage patterns over there. Okay, so the erosion is one of the reasons why this could happen. And then you have the antecedent drainage. What is an antecedent? That as Kuldeep pointed out, the transform fault boundary. Okay, suppose I'll just show. Okay, suppose this is your kind of a fault that is present. Okay, but during the long duration, there was a stream which was flowing like this. Okay, then suppose there is a disturbance between the due to the reactivation of this fault. What will happen is, now what will happen, that this stream will now flow over here, and there is a kind of a difference. You can see that this area has got disturbed. Okay, so tectonic, we talked about effects of tectonics on the river channel patterns and everything. This could be also one of the ways where you will see the the difference. So suppose there is an uplift due to fault reactivation or due to folding. Okay, and the uplift took place. Okay, so the previously that I showed, suppose this was how it was flowing. Okay, and this is the fault that is existing. Okay, now the way this stream is flowing, okay, the rate of the flow and the rate of the change, okay, due to this tectonic, if it's going to be similar, you will not see any disturbance in the pattern. Okay, it will flow in the similar manner. Okay, you will not see any disconnect. So that means tectonics have taken place over here. Okay, but the river is not showing any change over there. Or suppose say you have, you know, kind of an uplift over here. Okay, but the river, okay, how to show this? Suppose this is a block diagram. Okay, the river is flowing like this. Okay, suddenly there is, you know, like huh, so there is an uplift over here. Okay, there is an uplift over here, but the rate of the uplift is kind of similar to the rate of erosion of the river. Okay, so what will happen is, suppose, you know, there is kind of a hilly region that is formed here. Okay, there are like mountains formed here, but the river is still flowing in this orientation only. It has not changed the way it is flowing. Okay, so that is an antecedent drainage. Okay, so the rate of the cutting down by the river and the uplift is the same. So the river is maintaining its course. Okay, so the trend of that area has changed, but the river is not showing any correlation with that. Okay, so these are discordant drainages where the area has got disturbed. Okay, but it has not had an effect on the, you know, the way the river is flowing over there. And concordant is, it is flowing as you know, along the trends that are visible in that area. Okay, so many Himalayan region, Himalayan rivers are an example of antecedent origin. Okay, so these rivers were there even before Himalaya was created. Okay, mostly having their origin in the Tibetan area. Okay, but even with the uplift of the Himalayas, the rivers have not, you know, changed their direction. They are still flowing in the similar manner. Okay, so these are antecedent drainage systems. Now we come to the depositional features. Okay, so the first kind of depositional features that we see is in the middle course of the river. Okay, where the channels are meandering, we find point bars. Okay, bar deposits. Okay, these are usually forming along the channel, you know, along the channel edges or in between the channel. Okay, so you can see a longitudinal bar. Okay, so the water is flowing, you know, to from the sides of this bar. You have a transverse bar, you have point bars. Point bars are the one that are being created at the edges of the channel. Or then you have a diagonal bar. Okay, you have side bars, diagonal bars, you have sand waves. Waves, why? Because they are, you know, kind of forming the the curvature, sorry, it is forming curved kind of point bars. Okay, and you can see that the, you know, the crest of that sand wave is going to point towards your, you know, flow direction. Okay, you have mid channel bars and you have boulder bars. Boulder bars is mostly made up of, you know, very bigger sediment, bigger size sediments. Okay, so these are some of the bar deposits. These are depositional features that are created within the channel, within the riverbed, or on the sides of the river channel. Okay, then you have natural levees. We spoke about it in the starting slides, where due to the flooding stage, okay, where the water, you know, increases, the water level increases in the river channel, it will flow on the sides. The first deposit that is going to, the first kind of sediment type that is going to get deposited during this time is going to be the coarse sediments, and it is going to be at the, you know, banks of the rivers. Okay, so that with time, with recurring, you know, flooding over there is going to form levees. Okay, these are called natural levees. Then the next depositional features that we see are alluvial fans. This is usually, this forms when the stream is, it is coming from a higher elevation, or steeper regions, and the gradient suddenly kind of decreases. Usually these are found near the foothills of the mountain regions. Okay, so over here the stream is going to flow, and it is going to deposit all the sand and silt sized sediments along the sides of the river bank, of the river valley, or the drainage valley, or the drainage basin, and it is going to form a fan structure. Okay, this is different than delta. Deltas are created near the mouth of the river, that is the end stage, old stage of the river, and alluvial fans are created near the foothills. Okay, once the slope is kind of changing in its gradient. Okay, then we come to deltas. Okay, so deltas are usually formed, as I said, near the mouth of the river, or the old stage of the river, or the the lower course of the river. Okay, so the conditions that are going to, now deltas are not always formed wherever the river is kind of meeting a larger water body. There are some conditions which have to be met for the delta formation. So there needs to be a balance, and kind of concurrent vertical and lateral erosion, okay, in the upper part, in the upper course of the river, so that the kind of there is abundant sediment supply, which later on is going to get deposited in the deltas. So if there is not much erosion that is happening, or not much changes in the kind of channel patterns that we see, where a straight channel becomes a sinuous channel, then it becomes a meandering channel, then a braided channel. If this is not occurring, the chances of delta formation is decreasing, because the sediment load is not increasing with the increasing course or increasing stage of the life. Okay, and also there is no deepening or deepening of the river channel over there to carry the sediments with it. Okay, so you need to have both vertical and lateral erosion in the upstream or the upper course of the river for delta formation. Then mostly the coast should be almost like preferably tideless. Okay, so it has a longer time, it gets longer time to for the sediments to get deposited and stay over there and not get washed out by the tides. Then the sea, or the the shelf region, the continental shelf region, should not have a lot of gradient over there. It should be shallow. Okay, otherwise the load that is coming with the river, it is going to get deposited in the sea floor. It is not going to form a delta. Current should be not, should not be strong. Okay, and if there are any other large bodies situated near the mouth of the river, okay, so the water is going to get directed to that, and not towards the uh, coast. Okay, so the sediment load is also going to shift. Okay, so these are some of the conditions that have to be met for a delta to form with respect to a one river system. Okay, now we have types of deltas. You have bird's foot delta, arcuate delta, cuspate, and estuarine. Okay, so you can see that the bird's foot delta, actually it looks like a bird's foot, and it is much more it is like longer in nature. Okay, and the there is less wave and tidal action, so you can have longer kind of depositional features for the delta. Then you have the arcuate delta, which is it looks like that for what we talked about, the alluvial fan. Okay, so it will be like a fan shaped delta. It is curved, and mostly it has a, the coastline is pretty smooth due to the the wave action that is happening over there. So Ganges is a type of the arcuate delta. Okay, Mississippi is a bird's foot delta example. Then you have the cuspate delta, where it's a sharp kind of projection is have is formed at the where the water is kind of interacting with the sea. Okay, so these are mostly in the stable water body, that is sea or ocean. That means there is not much tide action or wave action over there. And then you have the estuarine delta where the deltas are partly submerged. Okay, in the coastal waters there's a delta, but it is submerged. Okay, so Amazon River Delta is an example of that. Now we come to one important aspect is that is the flood intensity. Okay, now the flood intensity is going to again depend on your drainage density and the kind of external factors like occurrence of vegetation. It is also going to depend on the course of the river that your that your stretch is present in. Is lagoon same as estuary? No, lagoon is not same as estuary. Lagoon is kind of that water is kind of getting input from both the river and your sea. Okay, it is the mouth or the the region where the fresh water is going to interact with the sea water is very narrow, but there is a big water body that has formed. Okay, but the interaction is very less. The area of interaction is estuary is where kind of the river is meeting the sea water. Okay, but there is a large area where it is constantly interacting, the fresh water and the sea water. Okay, like Chilika. Okay, Chilika lagoon, it's a lagoon. Okay, so Chilika lake is actually a lagoon. It is one of the biggest lagoons in I think it is one of the biggest lagoons that we have in India, as well as otherwise also it's one of the largest lagoons that we have. Okay, so it has both fresh water and interaction with the sea water. Okay, but the place or the region where this is interacting with the sea water, the fresh water, is very narrow. Okay, so that is a difference. Lagoon and estuary are not the same. Estuary has a constant interaction with the sea water. Okay, this is my rough understanding. I would suggest that if you are confused, then you can maybe see it on the Google. If I find something, some important material on this, I'll put it on the discussion forum. Okay, so
Yes.
now as I said, the flood intensity is going to depend on your drainage density, on the occurrence of vegetation, or the the air, the place where it is happening. Okay, so you have upstream and then you have downstream floods. Okay, upstream floods are going to, as the upstream area, okay, drainage density is probably going to be very uh, you know uh, the drainage density could be low over there. Okay, so upstream you can see that the discharge, that the high discharge that you see over here, okay, it's only for a very short period in upstream areas. Okay, but in downstream areas the high discharge is it can prolong, it can happen over a prolonged period. Okay, so upstream floods are short period floods, downstream floods are longer period floods. Okay, if you have a higher drainage density, there is more discharge. If you have a low drainage density, you have a lesser intensity flood. Okay, and then also the vegetation, if you have more vegetation, okay, so your flood intensity is going to decrease. Okay, and if you have no vegetation, your flood intensity is going to increase. Okay, so your discharge is higher over there. Okay, so channel density is going to kind of affect your discharge. Okay, and this is kind of as even in your weekly content, sir has spoken about the Kedarnath flood. Okay, so the Kedarnath area, the flood that happened in the upstream. Okay, so the upstream floods are usually due to sudden input of water like cloud burst or dam failures. Okay, so these things are going to cause upstream floods which are for shorter duration. But if you come to the downstream areas, okay, so these floods are mostly due to the channel migration that we see. One example is the Kosi river. Okay, over here you can see that channel migration is another, as we have discussed till now, how the channel kind of shifts from straight to sinuous to meandering, braided, and then again it can become a straight channel. Okay, so you can see over here that in the past years how the channel, the flow direction has changed for Kosi river. Okay, so you can see that the river originally was in the eastern part. Okay, in the it was flowing north to south, but from the eastern in the eastern part. Okay, with time you can see that it has changed, and now it is flowing through to from in the western part. Okay, why this channel has changed? Because of these processes. Okay, first there is erosion, there is then you have there's a bar which has formed. Okay, now because over here the deposition is going to increase. Okay, so now as the deposition increases, okay, the water is getting cut off from here. Okay, so now the channel has shifted towards your right. Okay, then again it will start depositing. After some time again this will join with this and the channel will move towards your eastern part or the right hand side. Okay, so the similar thing has happened over here. Okay, deposition, it started increasing in the right hand side or the eastern side, and the channel kept moving in the western side. Okay, that is why the floods that we see in Bihar is actually due to this channel migration process that is happening for the river Kosi. Okay, why the channel migration is so frequent in this area is because that region has very soft sediments. Okay, it is kind of in the alluvial yes, somebody has raised their hand. Do you have a question? Okay, so it is kind of happening in the lower region of Himalayas, where the alluvial fans are present. Okay, so it is easier for the channel to migrate through that alluvial fan. Okay, so these are what we learned today is how the fluvial geomorphology is kind of eroding, how it is transporting, how it is depositing, how all these processes are dependent. Okay, how these processes are dependent on the flow velocity, on the sediment supply, on the sediment size, sediment type, the amount of discharge. Okay, and then again there is a play between these aspects and the kind of the nature of channel patterns that are being created, how they are going to affect your drainage basin development, drainage density. Okay, then the kind of features that are formed, we studied about the erosional features where the predominant action is eroding. Okay, and because of the river erosion you are getting some features like canyons and river valleys and waterfalls. Okay, and then due to a balance of erosional processes and the depositional processes, you have levees you have point bars forming, you have levees forming, uh, then you have meanders forming, oxbow lake forming. Okay, and then you have depositional features. Okay, so obviously point bars and levees are also depositional features, and then deltas, alluvial fans, flood plains. Okay, these are all depositional features. And then we learned how after these are formed, channel can migrate due to due to the interaction between the erosional processes and the depositional processes. Okay. uh, Channel migration does happens within that river valley itself. Okay, so if the river valley area is pretty wide and the drainage density is also kind of in the moderate region, the channel migration is very much possible. Okay, and we saw the example, over here we can see that Kosi river is one of the examples where you see channel migration, and we also see the consequences of the channel migration. Okay, so for today, we have till here. If anybody has any questions up till now, you can ask them. I will copy paste the resources where you can find. Okay, so I upload the recorded lectures on YouTube. Okay, by tonight or by tomorrow morning, and it is also updated in the sheet that is now present on your NPTEL, the platform, in the sidebar itself. In the I think it's the last option where it is given as problem solving sessions. You can find the same links over there also, but you can kind of subscribe to the YouTube channel, so you will get a regular update whenever I upload the recorded session. Okay, and the Google Slides has everything from the week 1 itself. Okay, all the slides that I'm showing over here, all from week 1 is uploaded on that one slide link. Okay, so if anybody has any question, please go ahead. If you have any question regarding the previous assignment solution, or any question that is confusing you in the present assignment, I think assignment 4 that you have to submit in the coming week, you can ask now. If you have doubts later on, if you go through the material, you can ask in the discussion forum. One of the team members is going to respond. Okay, thank you, Kuldeep. Obviously, you can ask anytime you want. So, if you have no more doubts, if you have no more questions, then I will end the session here. Thank you so much for joining, and hopefully, this is helping you, and hopefully, the material helps you in solving the assignments. So, you can go through them. I try to summarize everything that is taught in your weekly content, and also the material is related to the assignment questions that you have, so you can go through the material and hopefully you can answer your assignment questions. Okay, thank you so much. Thank you for your kind responses, and thank you for participating and interacting with me today. Hope to see you in the next lively session, that is next Friday. Okay, thank you so much.